Good morning and welcome back to our last chapter. This is the first of 7 sections, and this chapter is on different types of equations. We're going to be looking at parametric equations, we're going to be looking at polar equations, we're going to be looking at vectors, and then the calculus about those. So each of them will be split pretty much into two. The first section will be describing what they are. Like this section is going to be describing parametric equations, and then the section after that will be describing the calculus on that type of equation. And so with parametric equations, they're fun because you can do all sorts of graphs. This graph that you see in the background is one graph. It's called an involute of a circle. And we could use all sorts of fun words like cycloid and hypercycloid and hypocycloid and all sorts of great ones. I had a couple more there. Where'd they go? The cissoid of Diocles. I mean, who doesn't want to graph that? The folium of Descartes. The witch of Ignacy, which you've actually seen before. You've seen witch functions before. Those aren't as exciting. The names are fun though. But we'll see how to graph this stuff. This was actually just graphed on my calculator. So we'll actually see how to do this at the end. And it's one of the assignment problems. That's where I picked it up from. And so, first of all, what is a parametric equation? A parametric equation is one where you split up the x dimension and the y dimension, and you define each of those by a third variable called a parameter, and we call that t. A lot of times t is for time, but it doesn't have to be. But we'll have x is something involving t, and y is something involving t. And we will find each of them separately. So we use t to describe both x and y. And believe it or not, you've actually most likely used parametric equations before. In physics, we talk about projectile motion. That's going to be a parametric equation. In projectile motion, we'll just start with just a ball being kicked. So we're starting at the origin, and it goes up, and then it comes back down again, where the y value is going to be the height, and the x value is going to be the distance the ball travels along the horizontal. So we'll just call that distance. But those could easily be just x and y. And you can define both of these by the third variable, t, for time. In your physics class, when you talk about projectile motion, you talk about how the height is going to be quadratic because of gravity. The height will probably equal something like negative 9.8 meters per second squared times time squared plus something minus something to get the vertex over where it is. We have the initial velocity, things like that. And then the distance will be something like it's moving it horizontally at 3 meters per second. This right here is a parametric equation because we're using this third t variable to describe the x and the y variables. So that's a crash course on what parametric equations are. Let's see some of them in action. So first, let's look at a parabola. It's kind of like what we were looking at. Graph and analyze the parametric equation. And so we have x equals, this is f of t, it's 2t, and y is g of t, it's 1/2 t squared minus 4. These are just giving the x and y function names involving t. That is not super important. Usually it's just x equals 2t and y equals 1/2 t squared minus 4. And then we have a window, a range for t. T is just going to go from 0 to 8, at which point it will stop. Generally speaking, t will stop. That's not always. It could go from negative infinity to positive infinity, or 0 to infinity, but again, most of the time t will be within a range. And so the first thing we need to do is we need to graph this. How would we do that? The same way we started graphing anything. We're going to plot points. We're going to start out with t values. T equals 0. If we plug in 0 to the x and to the y, we're going to get a point x comma y. This is graphed on the regular Cartesian coordinates. So if we plug in 0, x would equal 2 times 0, that's 0, and y would equal 0 minus 4. So we plug in 0, we get the point 0, comma, negative 4. Plug in 1, we're going to get the point 2, comma, 1/2 minus 4, that's negative 3.5. Plug in the point t equals 2, we're going to get 4 times 2 squared divided by 2, that's 2 minus 4 is negative 2. We're going to get 4, negative 2. So we can plug in all of those values from 0 to 8 to get a bunch of ordered pairs. And then we just need to take these ordered pairs and graph them, and then connect them with a smooth line. Like, we didn't plug in all the values. Like, we could have found any, like 0.7, 1.2. What about when t equals pi? I mean, we could find any value in there. It is a continuous variable. But in order to see what it's doing, we probably don't need to find all those values. So if we were to graph these, we would get this curve, which it's part of a parabola. Not much of a parabola, but it is part of a parabola. And we can see the different point values along the way. So one thing to know about parametric functions as opposed to regular functions is that they have a direction. T started at 0 and then it moved to 8. So notice these arrows here showing what direction it is that this graph is moving. Now, is that hugely important all the time? No, but a lot of times it'll make sense in the problem. When you kick the ball, it goes from your foot up and then to where it hits the ground later. And that is called the positive orientation. It's when it's going from the starting point, then as t increases, it's following those points that direction. A lot of times we'll end up with things that are going to be circular, and so knowing which way around the circle we're going is important. It's kind of like when we were looking at slope fields, which direction were we starting in a slope field could make all the difference on what that graph looked like from that point. From here, we could write this as its normal function equation. To do that, we are going to solve for t in one of our equations. This one would be the one to do it in, because we can get t equals x over 2, and then we're going to plug it in over here. So we'll get y equals 1/2 x over 2 squared minus 4. We can square those. X squared over 4 times 1/2. We get y equals 1/8 x squared minus 4. But then t goes from 0 to 8 because the domain is limited. Well, we can replace the t right here too. So 0 will be less than or equal to x over 2 less than or equal to 8. Multiply 2 in both directions. Usually we'd split this up to do it, but I think we can probably multiply 2, especially when one of them's 0. 0 times 2, so here x will be between 0 and 16. So we have the standard function, like just the regular function for the parabola right there, which is what we did, what we were graphed with our parametric equation. So that is in a nutshell, this is how you would graph a parametric equation. You'd plug in points. You'd plug in when t equals this, what will x and y equal? When t equals this, what will x and y equal? When t equals this, what will x and y equal? The more points you plug in, the more accurate it'll be. Something like this, I mean, we split it up into 8 sections. It's probably pretty good. We'll see how to do it using a calculator at the end, because sometimes that's almost necessary unless you're going to be plotting a lot of points. And it's fun. So, how about a circle? Graph and analyze the parametric equations x equals 4 cosine 2 pi t and y equals 4 sine 2 pi t for 0 is less than or equal to t is less than or equal to 1. So obviously we're not going to plug in 0 and 1. That will not get us where we need. However, we could plug in the eighths, 1/8, 2/8, 3/8, 4/8, because when we multiply by the 2 that's in the equation, that'll give us fourths. The fourths are pretty easy points to know for cosine and sine, because when you have pi over 4, you get the root 2 over 2 values. So we can plug in those values. So t equals all of those into each of them, and you can get those values. You guys can plug stuff in. I have faith in you. And then from here, you can graph it to get that equation, or to get that graph. So notice we started at that point right there, which is where we would normally start a circle, and we went in the correct direction that way around the circle. There's another example, I think it's example 3, that has a turtle is walking around a circle, and so you're just looking at what that looks like. It's a word problem for this. I didn't put it in here, but you can see it in your pages. If we wanted to write this as its function, well, it's not a function because it's a circle. If we wanted to write it as its normal equation without the t, this one would be a little bit tougher to solve for t. It would involve negative or arc cosines or arc sines. That's going to be a bit crazy. However, knowing what we know about a circle is going to be x squared plus y squared equals r squared. So let's look at what does x squared plus y squared look like. X is this 4 cosine 2 pi t. So we're going to have 4 cosine 2 pi t squared plus sine squared, which is again a 4 sine 2 pi t squared. We could square these to get 16 cosine squared of 2 pi t plus 16 sine squared of 2 pi t. Factor out the 16, and we get cosine squared 2 pi t plus sine squared 2 pi t. Now if we remember back to our identities, one of those important identities is the Pythagorean identity, which said sine squared of an angle plus cosine squared of an angle equals 1. These angles are the same, 2 pi t, 2 pi t. So this is just 1, which means x squared plus y squared equals 16, which is r squared because it has a radius of 4. So that's a slightly different way of writing the regular equation from the parametric equation, specifically when it's not going to be a function. Because when it's going to be a function, we should be able to get y equals something. When it's not a function, we have to be a little bit more creative than that. So let's look at something else. We have a parametric equation of a line. Talking about functions and writing equations, a parametric equation of a line, why would we ever need a parametric equation? We have a regular equation because sometimes the x and the y almost need to be taken separately. A parametric equation of a line is actually a fairly easy piece because if we have our slope, b and a, we're just going to have the y value times t for the y, right? Because it's rise over run. B is the y part of the slope. And a is the x part of the slope. So we just have a starting point plus the x part times t. A starting point plus the y part times t. And now this is not unique. Just like with a point slope form of the line, by picking a different point, picking a different starting point, we can have the same line with an equation that looks different. Here we could actually do the same thing by changing the slope. Now, not changing it, but unreducing it. So instead of, say, 1/2, we could have 2/4. That's going to get the same slope for all intents and purposes. In a regular equation, it would be reduced, but here when it's split up, the reduction does not necessarily have to happen. And same thing, instead of 1/2, we could have -1 over -2 and split it up that way, which would go the other direction. However, if it's just a regular full-on line, that doesn't matter. If it's a line segment, it's something we need to think about, however. So let's look to see what some of these could look like. We have the equation, the parametric equation, x equals -2 plus 3t, y equals 4 minus 6t, for just infinite, which describes the line. Find the slope-intercept form of the line. So we need y equals mx plus b. Well, we have our slope is going to be -6 over 3. And then all we need is another point. We have the point -2 comma 4. And so we just put that into slope-intercept or point slope form to begin with. Y minus the y part of the point equals slope. -6 over 3 is just going to be -2. X minus the x part of the point. So -2 becomes +2. Distribute that -2. -2x minus 4. Add the 4 over. Y equals -2x. 4's cancel. So this is the equation for y equals -2x. Goes through the origin. So being that it goes through the origin, we could have written the parametric equation as x equals 3t, y equals -6t, because it goes through the point 0, 0. But it was having us find the slope-intercept form of the line. Other thing that we could do, find two sets of parametric equations for the line with the slope 1/3 that passes through the point 2, 1. So this is going the other direction. So we're going to go the other way with the slope. B equals 1, A equals 3. And then here we have x naught and y naught. So we're going to have x equals 2 plus 3t, y equals 1 plus 1t. That's one way. We could find another point if we go up 1 to get to 2 over 3. We could also have the point 5 comma 2. We could plug that in. X equals 5 plus 3t. Y equals 2 plus t. We could have also changed, I have no idea what that line just showed up there for. It's the weirdest thing. We could also change the slope. Instead of 1, 3, we could use 2, 6. So we could have x equals 2 plus 6t, y equals 1 plus 2t. We could make it negative. X equals 2 minus 3t, y equals 1 minus t. So each of these is going to describe the exact same line in function form, but in parametric form, they're all going to look different. Here we just had to find two sets of parametric equations. We found 1, 2, 3, 4. So you have options there. And there are a lot of other options that we could have easily looked to as well. How about find the parametric equation for the line segment starting at P and ending at Q? So it's a segment. It starts at P, it ends at Q. I would look at it like, let's not look at the slope. Let's look at the change in X and the change in Y. So the change in X, we go from 4 to 2, which means that A could equal negative 2. And Y goes from 7 to negative 3. So Y, or B, will equal negative 10. Notice if we put this into a slope, it would have, the negatives would have canceled, would have had a positive slope, which would have gone from Q to P. But it's specifically directional, starting at P, ending at Q. So let's start there. And then our P, that's our initial point. So X equals 4 minus 2t. Y equals 7 minus 10t. And then it's always a good thing to know when, like, what is your window for t, because it is a segment. It starts and stops. So here, if we plug in 0 for t, we're going to get our initial point. So we know that 0 will be less than or equal to t, will be less than or equal to. What do we have to plug in to get our final point? Well, the way we did it, we just have to plug in 1. If we would have found a slope and reduced to have 1 over 5 or negative 1 over negative 5, t would have had to go from 0 to 2. So that just depends on what your equations actually look like. So, but that would be a set of parametric equations to describe that line segment. So there are a couple other applications to this that you'll see in the text. Now, none of them are particularly difficult. It's kind of like what we looked at. So, you plug them in and you get your X and your Y values. You'll start looking at like the cycloids and stuff where you'd look at it and think, wow, I don't think I could graph that by hand. Well, that's possibly true. I mean, you could, but it would take quite a while and might not be all that accurate. But one of the fun things about parametric equations is the ability to graph them on a graphing calculator and make all sorts of fun designs. You'll graph flowers and stars and hyperstars and all sorts of things. Involutes of a circle. So for that, by the way, or actually for any of these, to graph any of these, the first thing that you're going to want to do is you're going to want to hit that mode button and set it to parametric. When you do that and you go to y equals, it's going to switch already to give you your x and your y. When you enter stuff in and you hit that variable button, it won't be x anymore, it'll be t. So it does all that for you. Now, if you just graph it, you're probably not going to see what you want to see. You need to change the window setting. Specifically, you're going to want to change your t's. A lot of times it'll start out at 0 and go to 2 pi. As soon as you move the cursor from 2 pi, it'll change to 6.28 blah blah blah. I would type in 2 pi. You can do that. The t step will set itself automatically, usually to right about here. That's just how often is it going to find that value. It'll plug in a value for t at every 0.13, which most of the time it's going to be plenty. But that'll usually, again, it'll usually set itself, so you don't have to worry too much about it. If you are graphing something amazingly complicated, it might take a long time, but it's usually good. And then your X and Y windows, those you're going to want to change based on your equation. Like a lot of times I'll graph one, and then I'll see where it needs to be, and then change my X and Y windows so that it matches. And things to change for your T, sometimes it'll tell you what you want your T values to be. Sometimes it won't. You can experiment with that. A lot of times it'll start overlapping itself at a certain point and just keep going over the same thing over and over again. This is the equation that I graphed for the front page of this, and it's the involute of a circle graph. For my t's, I went from -40 to +40. Now, you didn't see all of that negative and positives because it went off my graph, which was the intent. But I did have to go negative. Otherwise, you miss that piece at the beginning that was, or that piece in the middle that looked, I can't graph, it looked kind of like that at the middle. It kind of gave you a little heart. When it went just the positives, it was a spiral. So the negatives sent it around the other direction, which gave it the cool look that it had. So this is what we're looking at this section. Again, it's an introduction to parametric equations. You'll be graphing some by hand. You'll be writing, going back and forth, and you will be graphing using a calculator. You won't be doing any calculus or anything in this section. We'll look at calculus next time. But until then, keep asking questions, keep working problems, and as always, happy mathing.